Thank you for attending this presentation. My name is Lorena Poenaru-Olaru, and today I'm going to talk about my work into sustainable machine learning retraining, in which we try to optimize the energy efficiency without compromising the accuracy of machine learning systems. Oh, no?
Is it on?
Yeah.
Okay.
I think so. No worries. Should I do it again?
Sure.
Okay. So, hello everyone. Thank you for attending this presentation. My name is Lorena Poenaru-Olaru, and today I'm going to talk about sustainable machine learning retraining, in which we try to optimize energy efficiency without compromising the accuracy. So, let's start with understanding which research field is this subject coming from. So, it's actually part of the green AI research field, in which we try to create energy efficient AI machine learning systems. And probably there's no surprise for anyone, AI systems are quite energy intensive, and especially during the model training, in which the model is learning the data, and also during model inference, in which the model is just making new predictions. So, but according to this source, the model training is one of the most energy intensive parts of the machine learning process. And let me tell you something, the AI ML systems require to be updated over time through retraining. So basically, it's not only once that you just train a machine learning system, you need to retrain it over time. And let me explain why. So let's assume that we have this machine learning system, which already was trained with the training data. You deploy the system into production because everything is okay. And then you start testing it, you start the inference part. And you inference in each period of time. So for instance, you want to get monthly predictions for some use case. And the problem is actually the real world data is changing over time, which is something that we call concept drift. And because of this, the model becomes outdated because the data becomes significantly different than what it actually learned on. When the model is outdated, it needs to be updated through retraining. And this is actually energy intensive because, and in this study, we want to see what are the least energy intensive methods to retrain machine learning systems over time. So let's start with the first set of techniques regarding the retraining frequency. There are two techniques that we can use regarding retraining frequency, periodic retraining and concept drift detection-based retraining. And let me explain a bit the difference between them. So let's assume that we have this model trained with data until December, and we need predictions for the upcoming months. Well, with a periodic retraining, when the data from January will be available, we would retrain the model. We'll do the same when the data from February is available, and so on. So basically, this is periodic retraining. With the concept drift detection-based retraining, we don't actually retrain every month, but every month we check if there was a change in the data. If yes, then this is the moment when we're gonna retrain the model. So basically, this technique lowers a bit the number of times we need to retrain a model. So, and let's go to the second pair of techniques from the retraining data perspective techniques, where we have full history retraining and sliding window retraining. Let's go again through both of them and understand what's the difference. Through full history retraining, we are training the model once, and then when new data comes in, we add this data to our old data and we retrain the model, and we do this over and over again. Well, for the sliding window retraining, we discard all the old data and only retrain on the newest data. So basically, we always make the training data a bit smaller. So we can assume that the sliding window retraining is a bit more energy efficient because the models trained on smaller amount of data are more energy efficient, so more sustainable. So let's go to the research questions and goals. In this study, we empirically evaluate these retraining techniques in terms of both energy, both the energy they consume and the model accuracy. And we answer the following research questions. First of all, what is the impact of retraining of each retraining technique on the retraining energy consumption? Here we analyze periodic versus concept drift detection-based retraining. and also full history versus sliding window retraining. And second of all, we also analyze what is the impact of each retraining technique on the inference of the energy consumption, if there's any. As a methodology, we perform a case study. We use 3 machine learning systems, all of them derived from the AIOps research field, and all of them regarding failure prediction. And we also analyze 3 drift detection techniques. So these are more details about the models that we built. So one mention is that one model is created for monthly prediction, the second one for daily prediction, and the third one for weekly prediction. And the way we split the data is that we split it in half. We use the first half for the initial training, and the second half, we split it into testing batches. And then with this part of the data, we perform the retraining experiments. In terms of energy measurement, we measure the energy at the concept drift detection level. So basically, every time we perform concept drift detection, we measure the energy. We measure the energy for the initial model training, as well as we cumulate this energy to the energy measured for the future retrainings. And we also measure the energy at the inference level. So let's look into how we measure energy from the lifecycle level. For periodic retraining, after each testing batch and after each retraining, we measure the energy and then we make a cumulative energy. And with the concept drift detection-based retraining, we only measure the retraining energy after concept drift is detected, because that's when the concept drift, that's when the model gets retrained. So these are the results for the first research question, but I'm going to guide you a bit through them. So when we analyze the full history versus sliding window retraining, some interesting findings that we can make is that in most of situations, on the top plots, you can see the raw KFC, which is the model performance. And on the bottom plots, it's actually the energy consumed. So if you look at the arrows, you can see that in most situations, the accuracy of the model is not significantly influenced by using either full history versus sliding window retraining. But the energy consumption is actually totally different in terms of full history consuming much more energy than sliding window. So in some situations, the sliding window approach achieves similar performance as full history while consuming less energy, and that's how we conclude that a sliding window approach consumes significantly less energy than the full history approach. When we look into the periodic versus concept drift detection-based retraining, so basically the 3 pairs in the middle of each plot versus the last pair at the end of the plot, we can also notice some differences. So let's look into this example. Here, the model performance is actually the same for periodic and concept drift detection-based retraining, which is something that we would want, a much higher performance. But the energy consumed during concept drift detection-based retraining is a slightly bit higher than the periodic one. And why is this? Because the concept drift detector is too sensitive, and basically it says that the model requires retraining every time. And then to this, you also need to add the concept drift detection energy, consumed energy. Then we also have this situation in which the concept drift detection-based retraining is very similar to the static situation, in which the static situation shows a model that's retrained only once and then never retrained, which shows that the model did not improve in accuracy, but also it didn't increase the energy consumption that much. And what would this tell us is that the energy consumed by this, so that the concept drift detector actually did not manage to capture any change in the data, and said that there's never the need to retrain, which is not too sensitive, but the opposite. A compromise situation that we can see here is this situation in which the concept drift detection, the energy consumed by the concept drift detection retraining is lower than the one consumed during periodic retraining. but the accuracy is slightly smaller. So this means slightly lower. So this means that the concept drift detector still improved the energy, but also decreased a bit the accuracy. And what we all wish is an ideal situation in which the accuracy of periodic retraining and concept drift detection based retraining are kind of the same, but the energy consumed for concept drift detection based retraining is lower. So this is something that we would want. So remarks from this experiment: some concept drift detectors are too sensitive and detect everything as drift, which is equivalent to periodic retraining. Some concept drift detectors are not able to identify drift at all, so this is equivalent to never retraining the model again, but this is still bad for the model accuracy over time, so not practical. And basically from this, we can say that concept drift detection-based retraining is not always better than periodic retraining. And basically, concept drift detection-based retraining usually consumes less energy than periodic retraining, but you need to choose the concept drift detector carefully. So for the second research question, when we look at the energy on the inference, we did not necessarily notice any significant change. So basically, we can say that the retraining techniques do not impact the energy on the inference. And in general, so the conclusion from this research question is that in general, the employee retraining technique doesn't affect the energy consumed during inference tasks. So main takeaways from this study: if you want to create sustainable machine learning system over time, and the accuracy between sliding window and full history is the same, try to go for the sliding window approach because this will save you some energy. And also, if you want to create a sustainable machine learning system over time, choose a concept drift detection retraining technique only after you make sure that the concept drift detector is suitable for your use case and for your data sets. So with this, I would like to conclude this presentation and would like to thank you for your attention. Thank you.